Welcome to the final thing of the week, apart from the post-celebration.
Okay, so thanks everyone for staying to the hopefully not bitter end. Okay, so my goal today, so first I'm going to finish off the proof for C5. We did all the setup yesterday, and then I'm going to kind of move forward to the stuff that's happened in about the last 2 years. And I'm going to kind of focus on one result, but I'll give you kind of the big picture and then focus on one theorem, and I'll see how far I can get through that. So I'll try at least to sketch the idea. Okay, so just to remind you what so this is the theorem, first theorem, Erdős-Hajnal holds for C5. And remember, this is the tool, or a tool that we're going to use. So this says if I have A and B, and degrees from A to B are at most delta, then one of two things happens. Either I can get a nice big comb, either I can get a nice big comb. Big meaning I've got some number at the top, but the size at the bottom is n over t to the k. N is just any number that I stick in here. Or the expansion is not very big. In other words, the portion of B seen by A is not very large. And okay, it's what it comes out as, so this expression. You can choose k, yes. So pick any k you want, and then k bigger than 1, I think. Good, okay, so let's go for the proof, and what's the goal? So the goal is to find something that looks like this, so kind of a nice big cone like so, where this set is independent. And if we can do this, so if we have this sort of polynomial behavior, so t of them the size n over t to the k, then we're good, because we can use this quasi-Erdős-Hajnal idea. So it's just like strong Erdős-Hajnal gives a linear size pair. Quasi-Erdős-Hajnal was the set's a polynomial size. Polynomial in what? Well, n over some polynomial in the number we have. Okay, so we'd like this, and if we get this, then it tells us immediately, aha, I don't have any edges like that, because that would give me an induced C5 just running up around the top. So these sets are pairwise anti-complete, and if we're at this sort of size, then we're in good shape, because we're set up for quasi-Erdős-Hajnal. Okay, so how are we going to do this? So, okay, why don't we start with a vertex of maximum degree? That's hence my use of delta. So start with a vertex V of maximal degree. Let's argue by it. I'm going to modify this in a second, but here's a sort of first attempt. Let's just argue by induction. Okay, so I get some, I apply Erdős-Hajnal in the neighborhood. I know that by induction. I get a big clique or independent set. But there's already a problem that, okay, if I get a big independent set, I'm happy, because then I can say, okay, this maybe expands poorly to the rest of the graph. So this is going to be the strategy. I'll find a large independent set. I'll say that expands poorly to the rest of the graph. And now this whole thing, I've got an independent set, and I can kind of cordon it off with a reasonably small number of vertices, and then I can repeat in the rest of the graph. So that's going to be my target. The problem is that when I apply my inductive statement here, I might end up with a clique instead. And that's no good to me for this game, because if I've got lots of edges here, that just sort of pushes the problem down. Okay, and you can kind of play around in the bottom and see what you get, but it's not as helpful. Okay, right. So let's do something different, slightly different. So improve by induction on size of G, that alpha of G times omega of G. So we'll sort of actually get some trade-off between alpha and omega, so that the product is at least G to the tau for some small tau. And I'm not going to worry about what the actual number is. It's just some small quantity. Okay, and this is good because it says either I'll get quite a large clique or I'll get quite a large independent set, and I have a trade-off, and that's going to turn out to work nicely. Okay, so start with, okay, maybe I won't ask this question to the audience again. As usual, start with Rödl. So, and if necessary, complement. So C5 is nice and self-complementary, so we can assume that we are sparse, meaning that maximal degree is at most some small constant times n. Okay. Right. So now we'll do exactly as we planned here. So we'll start with a vertex V of maximal degree. And we'll find an independent set in here. Okay, so A. And A is going to be, well, I know that I write H for the subgraph induced by neighbors of V. And we know that, so by induction, you know that alpha H, omega H is at least, okay, mod H to the Tor. In other words, alpha H is at least delta to the Tor over omega H. Actually, I may as well throw an omega G here. Okay, so I'm sort of giving up a little bit here, but not very much. Maybe not very much. Okay. Right. And now let's look at B, which is the neighborhood of A, or minus, so the stuff outside, stuff distance 2 from V that's adjacent to something in A. Okay, so apply the Combe lemma. So by Combe lemma, so either we get okay, I haven't said what K is. It doesn't really matter too much precisely. If you want, let's set K as 2, but okay. Let's just set K equals 2, but I'm just going to leave it as K for the moment, and it's not sensitive to the value we pick. Okay, so by the Combe lemma, either we get T and over T to the K comb, in which case we're happy. We're in the strong Erdős-Hajnal, in the quasi-Erdős-Hajnal world. Or, okay, how big is B? Is at most some constant times delta to the 1 over K and to the 1 minus 1 over K. Okay. Right. Okay, so that tells us that if I look at V and the neighborhood of, well, yeah, V and the neighborhood of V and B, so kind of all the stuff that's currently in the picture, so that's at most 1 plus delta plus whatever this constant is, delta to 1 over K and to the 1 minus 1 over K. Okay, yeah.
I guess n and delta are switched. I don't know if it's there or here.
You're right, yes.
K is 2. So. Oh, yeah.
By accident, but it, yes, okay. Just for consistency, thank you. N to the 1 over K, delta to the 1 minus 1 over K.
Presumably here n is the number of vertices outside the independent.
N is the whole graph, always.
Always.
Yeah, yeah, because that's our kind of goal, is to get n to the Tor as, yeah. Okay, right, so n's much bigger than delta. And if you kind of add up exponents, you get 1 here. So this last term is dominant here. That's the most of the weight is there. So that's at most some other constant times n to the 1 over k delta to the 1 minus 1 over k. Okay. Right. Okay, so I mean the numbers are what the numbers are. It's just we kind of chase through the consequences. And now the idea is, okay, I'll sort of take all of this set A, I'll delete it, and I will repeat with the rest of the graph. Okay, so in fact this is going to be somehow, you know, delta 1, and now here there's going to be maximal degree, okay, some slightly smaller delta 2, and I'll do the same thing again, and I'll just keep repeating this. So I'll find a vertex of maximal degree, I'll look in the neighborhood, I'll find a largest possible independent set, I'll check that either I get my comb, in which case I can go home, or it expands poorly, in which case I'll say, right, you know, I've got that bit, I will remove that and then carry on with what's left. Okay.
The thing you've removed is the thing in this picture on the left, so V in the neighborhood and B.
Right, so we remove V and the neighborhood of V and B and just iterate or repeat. Okay, so we get sort of delta is, say, delta 1, delta 2, and so on. We get this decreasing sequence of deltas, and each time we get whatever we get in terms of so we get sets sort of A1, A2, and so on, independent sets. And we get AI that we get. Yeah, okay. At stage I, how much do we remove? Well, it's at most C double prime n to the 1 over k, delta I to 1 minus 1 over k. Okay. Okay, so now you do a little analysis and just see what that gives you. Rather than doing all that analysis, why don't we just assume all the deltas are the same? So I'll just do the kind of really nicest possible outcome. All the deltas. So suppose, for niceness, I should be doing binary search on the chalk. For niceness that all delta I are equal. Okay, it's not cheating very much. So how many stages do we go through? So the number of stages, so is sort of n over, okay, how many do we delete at each point? N to the 1 over k, delta to the 1 minus 1 over k. Okay, which is, okay, with a, I'll just start numbering my constants, I think. So it's going to be, C is going to be different every line, so I'll it's just a constant. Okay, which is some constant times n over delta to the 1 minus 1 over k. Okay. Right. Okay. On the other hand, so these sets AI, why was I deleting everything? So the point is that I can now just take a union of the AIs. So I get a nice big independent set by taking a union. There's not even any cograph business here. It's just genuinely an independent set. So union of AI is independent. So, okay, what is alpha of G times omega of G? So how big was so alpha was at least So each one was at least delta to the Tor over omega of G. So that's size of AI. And then we've got and can I put a C3 out front just to take care of any constants? I've got an n over delta, so 1 minus 1 over k. So this is number of AI, so the number of steps that we're going through. And I've got my factor omega as well, times omega of G. OK, so the omegas cancel, so that's at least some constant times delta to the Tor, n over delta to the 1 minus 1 over k. OK, and as long as 1 minus 1 over k is bigger than Tor, that is at least n to the Tor. OK, in fact, I can absorb the C as well if I want. OK, but I'll keep the C. OK, so you can think of this as just a way of replacing deltas with n's because it's the same power. Good. So that's the inductive step. So you repeat, 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 and then take a union of these sets. OK, how did I cheat? Well, I assumed that all these delta i's were the same, whereas, of course, what you should expect is that every time you pull something out, what's left gets a bit sparser, so the deltas will be decreasing. But it's, again, it's an easy piece of analysis just to write down the bounds. OK, so yeah. Good. I'll kind of remark that we did use the fact that C5 was self-complementary here. So just kind of stepping back for a second. So we used that when we applied Erdős, and then assumed that we had a graph that was sparse. Okay, so I mean, and used the fact that we were in a reasonably sparse graph, and that was good. So that it meant we could do this whole business and not eat the whole graph in one go. It sort of breaks it up nicely. Right, if you haven't got C5, well, you can play lots of games with this sort of argument and sort of say, OK, what happens down here? How do things connect up? And you can get some results for pairs of graphs if you exclude something dense and something sparse. So here, the dense thing is C5, and the sparse thing is a complement of C5. It might be the other way around. But of course, they're the same. So it's good. Yep.
Which a priori is smaller than
OK. So yeah. So exactly here, the key thing is that we're looking at alpha times omega, and that's the thing that we're. So it's this quantity we're looking at rather than singly alpha or omega. So we need to have this trade-off to make the argument work. Otherwise, the world could be unkind to us and push us in the wrong direction. So. OK, so this C5 was sort of the state of play as of a couple of years ago, but there's been some more progress. We managed, so with, we managed to prove some more things. So let me kind of say what bounds there are for in general. And I'll do it by what the bounds are. So there's e to the root log n. So I'll tell you what the bounds are, and then I'll sort of indicate something about the proof and say what I'm actually going to talk about for the rest of today. So e to the root log n, log n, that was for all h. And that was, so B is for Butich, N is for Nguyen, and that S is for Seymour. OK, and the other S is me. OK, so for all h, we've got this sort of, again, small improvement in the exponent for all graphs. For paths, so this is with Paul and Tung. By the end of this lecture, there's going to be a huge pile of little fragments of chalk I've Reduced it to smaller. Okay, so there we can do, okay, let me write down what we can't do, and then I'll write down what we can do. So we can't do e to the constant log n. That would be Erdős-Hajnal. We'd be very happy if we could do that. Okay, next best thing, maybe you can do something that's close to log n. Okay, so log n to the 1 minus little o1. Okay, and depending on how you want to look at this or sell this, this either looks really, really close to Erdős-Hajnal or a really long way away. So, it's, I mean, really, really close, because look, we've almost got log n here. But that little o1 is up in the second exponent, and that hurts. I mean, it's again, this is sort of our intuition. Well, I can't speak for you, but my intuition works very well in this level, but it gets up to this level, and I just think, oh, that's going to hurt somewhere. But I don't have a very clear sense of the numbers. If I sit and stare at it to double check. Okay. And then the sum graphs we can actually prove Erdős-Hajnal for. So infinitely many prime graphs. So, okay, so I should say, again, I'll talk this down and up simultaneously. So the graphs aren't very exciting that we can get here. So it's not that I'm claiming we can get a bunch of graphs that you look at and think, wow, you know, I wanted to know Erdős-Hajnal for those. But the point is we can get infinitely many of them. So previously, you know, there was P4, there was K2, which you can think of as a special case of P4. There was the bull. There was this result I've just been talking about, the C5, and that was it. Those were the only kind of minimal graphs. Everything else you get by substitution, complementation, dropping to induce subgraphs. Okay. So now we've got sort of infinitely many basic examples that you can't decompose into smaller things. So again, it's a sort of small piece of positive evidence. We can do bounded VC, not vice chancellor, wait, VC, there we are. If the hyphen is between the V and the C, it's vice chancellor, and, or venture capital maybe. Okay, so bounded VC dimension, which is what I'm going to talk about the rest of today. I'll kind of come back and talk about that a bit more in a minute. So classes with bounded VC dimension. So it's not actually a single H here. You can reduce it to 3 H's. So yeah, so this is a classes with, yeah, so strictly speaking, it's not a single H. So just to say, but it does sort of fit here. And then finally, P5 we can do it for. Okay, so this near Erdős-Hajnal we can do paths of any length. And again, this is just forbidding the path. Not, remember, we know strong Erdős-Hajnal if you forbid a path and the complement, so something sparse and something dense. Here we're just forbidding something sparse. Okay, and then P5 we can do exactly. And again, that's the same group again. Okay. Right, that's yeah.
For C7, is there anything better than the general result?
Sorry, for P?
For cycles.
For cycle? Yeah, we don't have anything for, that's a good question though. Okay, let me say a tiny bit about the sort of proofs. Basically, the sort of proofs that use correspond to the functions you're getting out, the bounds you're getting out. You shouldn't be surprised that the types of technique you use, well, the bounds you get out depend on the type of techniques you're able to use. Okay, so this e to the root log n log n bound. So that's got by, so we talked about I showed you the Erdős-Hajnal argument for finding a dense or sparse bipartite graph. So we have a kind of slightly souped up way of doing that. And then the other thing that we do is we build, rather than just a bipartite graph, we build a multipartite dense or sparse graph. So we sort of iterate it, building it. So there's a sort of bipartite lemma. Plus kind of multipartite things going on where we try and make everything sparse or everything dense. Okay. So that gives the kind of root log log n. It might push a little bit further, but probably not for general. Probably not much more for general H. Okay. This one, the e to the near Erdős-Hajnal, e to the log n to the 1 minus little o1. So we do a completely different thing. There's, okay, what was known before? So there was the e to the root log n from Erdős-Hajnal. There's a nice result of Blanco and Bucic, where they got e to the log n to the 2/3. And that was using a kind of heavy structural argument. So they kind of really pushed the structural approach. And again, it does log n to the 2/3, but it doesn't seem to extend to longer paths or to get much past that. Okay, we use a different argument. So I mentioned the jar-fash path argument once or twice. So it's a sort of variant of the jar-fash path argument, except the jar-fash path argument, you're usually, okay, roughly speaking, you kind of walk into a graph. So it's usually in some sparse world where sparsity is measured either by cardinality or by chromatic number of neighborhoods. And you say, there's the big bad universe out there. I'm going to run out and explore it. And I'm always going to walk towards the big piece. So I'll sort of wander into the big part of the universe. And oh, look, I'm generating a path as I go. Okay, so that's sort of, with no detail, that's a kind of jar-fash path style argument. Here, okay, as usual, we start by applying Erdős. What happens? You're sparse or you're dense. If you're sparse, you're laughing because you're exactly set up to do a jar-fash path style argument, or to use, we did tree and anti-tree, the arguments from that. But it's not too hard. The problem is you might be dense. So what you end up doing is saying, okay, I'm going to walk slowly into my graph. I've got a huge piece of the graph that I've seen already. I've got a tiny piece that's non-adjacent. And as I kind of walk into this smaller and smaller piece, so it's somehow kind of inverted, that rather than walking towards the large part, you're walking towards the ever smaller part. You have to kind of really keep control of adjacencies and covers in that small piece of the graph. Okay, so that's just a kind of hint. That's not a hint of the flavor. And then the other thing, there's a kind of bootstrapping argument. So we prove actually e to the log n to the 1 minus 1 over k by induction on k. So we get an e to the log n to 1 minus 1 over k. Then you can start with that being your sparsity or density or whatever. Well, okay, let me not say. So there's a way of kind of putting it in recursively. It's a bit twisty. Okay, so that's this sort of near Erdős-Hajnal. And then the polynomials, so these all use something that, as a kind of shorthand, we're calling iterative sparsification. Okay, so that's what I really want to tell you about for the rest of today. Okay, right. Yes?
Do you have anything better than what works for everyone for the graphs that are self-complementary?
No.
Because then
No.
you can...
No, and in some sense, if we did, I mean, you could have any graph you could embed, you could take, I think you could construct something that contains it and its complement and is self-complementary. With a kind of few minutes thought, I'm sure that's possible. Yeah, okay. So if you knew it for self-complementary, then you'd know it for all graphs. Good. Any other questions before I move on? Okay. So let me talk about VC dimension. So, and this is kind of my last topic. Okay, so I'm hoping most of you have seen VC dimension, but if you haven't, let me say VC dimension is a wonderful thing. It kind of crops up in lots and lots of different places. So kind of computational geometry, there's this thing called learning theory that people always talk about. It crops up also in model theory, interestingly, and a lot now in combinatorics. So it kind of, it's a way of sort of measuring complexity in some sense. Let me just define it. So a set system, so it's sort of been around since the 1970s. So VC of Vapnik and Chervenienkis. So a set system F, here's the idea. So shatters a set A. So here's my set A. And I just look at the ways that, oh, it's nice purple. I look at the ways that, so a set system is a collection of sets, and I look at the ways that F intersects A. Okay, so set system F shatters a set A if I look at all the intersections, so F intersect A, F in F, it's actually all possible sets. So if I can get any set I want just intersecting with my fixed set. Okay. Right. And the VC dimension of F is the largest size of a set such that F shatters A. Okay. Yeah, there's lots of nice theorems about VC dimension. It's really, so the Sattershall, but there's also nice things about dual VC dimension, about sampling. It's a really nice topic. So if you don't know about it, I really recommend going and finding out about it. And it's also become quite a thing to kind of prove various kind of big combinatorial problems in the setting of bounded VC dimension. It sort of, it makes things nicer in some way. Okay. Right, that's VC dimension of a set system. So, ideally, I'd like now to have an hour to talk just about VC dimension, because I like the topic, but I'm not going to, and I'm actually not going to use very much about VC dimension. I'm going to use one consequence of VC dimension. Okay, right. VC dimension of a set system. What about a graph? So the VC dimension of a graph graph G is the VC dimension of just a collection of neighborhoods. So gamma V, V in VG. Okay, what does that mean? What does it mean to have, let's say, VC dimension at least 2? This is really telling you something about bipartite structure, sort of induced bipartite structure. So what does it mean to shatter a set of size 2 here? So let me just sort of translate this quickly. What does it mean that this set is shattered? Oh, by the way, I put open neighborhood here. If you put closed neighborhood, it doesn't make much difference. It's a plus or minus 1, so it doesn't matter which way you define it. Okay, what does it mean to shatter this set? So it means that I can get my neighborhood, I can pick vertices whose neighborhoods intersect this set in any way I want. Okay, so there's somebody that sees both of them, there's somebody that sees the top one, and not the bottom one, there's someone the other way around, and then there's someone that sees neither of them. Okay, so it tells me there's a certain bipartite structure. So VC dimension at least 2 says this bipartite structure exists, so sort of A and B here, and also that it's bi-induced, meaning that we look at the edges going across. We don't care what happens on either side. So kind of inside there is just a big question mark. I don't care whatever, complete, independent, and similarly on the left. Okay. By the way, just a kind of in brackets, if you have very large VC dimension, then you can just, by a little bit of Ramsey, make the left and right-hand side either complete or independent sets, but you can't choose. So you might be both complete, you might be both independent, or one complete and one independent. It doesn't matter which is complete and which is independent, because there's this dual VC dimension that allows you to switch between the two sides. Okay, so saying I don't have large VC dimension says I don't have this large bi-induced structure, and again, sort of in brackets, because I don't want to spend too much time on it, that's equivalent up to changes of constant to saying there's a list of 3 graphs that I don't contain, a bipartite graph, the complement of a bipartite graph, and a split graph. So a split graph's just bipartite, except you fill one side in. Okay. So, right. So this says A is shattered. And in general, if I want to shatter a set of size k, then I'm going to need 2 to the k vertices to do it. I need to get all possible intersections. Okay. Right. Need a date. 16. So what can we say about the Erdős-Hajnal property for graphs of bounded VC dimension? In other words, I fix some D, and I look at the class of graphs with VC dimension at most D. So class of graphs with VC dimension at most D has, okay, I'll say it slightly informally, it has cliques and independent sets. So Erdős-Hajnal property would be n to the constant. They proved near Erdős-Hajnal, so e to the log m to the 1 minus little o1. Okay. Okay, and they conjectured the Erdős-Hajnal property should hold. Actually, it was conjectured by sort of 2 groups. So Foxpack and Soot conjectured it, and it was also conjectured in the model theory from the model theorists. So that was Chernikov, Starchenko, and Thomas. Okay, so we've got conjecture coming up, and of course, as I've, it's not a big reveal because I actually have it up on the board already, but so theorem, there's classes of bounded VC dimension have the Erdős-Hajnal property. Okay. Right. Okay, maybe before I kind of erase these from the board, I'll say sort of these 3 results, they've all got the same general strategy, but the kind of details of how we do it differ quite a lot. So I'll say sort of there's one strategy that's used in the infinitely many prime graphs, which is a kind of, it's a sort of, I don't know, a local amplification strategy in some sense. And then these 2 actually use a very similar approach, except the details are really quite different, and P5 is much harder. So sort of the nice things you get for VC dimension aren't so nice when you forbid P5. Okay. Right. Actually, so let's go back to Erdős theorem. So before I talk about what the strategy is, so I mean, this iterative sparsification is going to be, rather than jumping to Erdős-Hajnal in one go, you kind of refine, getting your graph sparser and sparser or denser and denser, so you're kind of dropping to subgraphs. But let me approach that through an iteration. So let me remind you of Erdős. So Erdős theorem says, so for all h and epsilon, it exists a delta such that if G has n vertices and is H free, I'm writing this very informally, but I hope it's all clear, implies there exists induced subgraph, so linear size, induced subgraph with density either less than epsilon or bigger than 1 minus epsilon. So you can drop to a linear size piece, and it's very sparse or very dense, any constant you want. Okay, now, question is, how does delta depend on epsilon? So the Semradius regularity lemma proof, okay, so I'll just say large constants, but that's a euphemism because Semradius regularity lemma is involved. Okay, so gigantic constants. There's a nice paper of Jake and Benny, Fox and Sudakov. Do I have the date right? Yes. They managed to get something like, so much better bound, so essentially a proof that didn't use Semradius regularity lemma. And in some sense, any proof that you do that doesn't use Semradius regularity lemma, you can sort of, odds are you could lay a bet that you will get better constants than using regularity lemma. Okay, so they got something of form epsilon to the log 1 over epsilon. Well, actually, we can do slightly better, but only by a sort of log in the exponent again. So sort of the arguments that gave e to the root log n log n also give a slight improvement here, which I won't write down. But what's really nice is they conjectured, actually, that the exponent here should be a constant. Okay, so they conjectured polynomial. So i.e., for all h, exists a k such that we can take epsilon to be, say, delta to be epsilon to the k. Okay, it's a lovely conjecture. Okay, so actually, why is it a lovely conjecture? So So first thing to say is it implies the Erdős-Hajnal conjecture. So let's see. If you take epsilon to be some small negative power of n, so eta, some smallish power n to the minus eta, then what does this give you? This will give you a polynomial-sized piece of the graph where the density is less than n to the eta, and is n to the minus eta, or in the complement, I don't mind which, but let's think about the sparse case. Okay, and if the density is less than n to the minus eta, well, you can only actually greedily pick out an independent set, and you will get one of polynomial size. Okay, so, or, I mean, if you want to go probabilistic, pick out a tiny n to the sort of something very small and eta over 2 or something, and you're unlikely to hit edges. Okay, so I'll just say kind of, there's an exercise to check that this implies Erdős-Hajnal. But even better than that, this sort of interpolates smoothly between Erdős-Hajnal, well, between Rödel and Erdős-Hajnal. So the point is that it works at all scales. By taking epsilon to kind of shrink, you go from, epsilon is a constant, well, then you've got Rödel's theorem. It tells you that. Epsilon is some negative power of n. Now you're in the Erdős-Hajnal world, but this tells you kind of all the intermediate scales, something nice should happen. You get this sort of polynomial behavior.
Alex?
Yeah.
I'm sorry. So when you do this Rödel, for instance, don't you require that n is big? So epsilon and delta are fixed. And then you say if n is large enough, then such and such.
You can hide everything in the k. You can hide everything in the power, so.
Yeah, so the question is, so when you say that it's epsilon with k, you don't have to require that, so it looks cheating to me that you take epsilon as a function of n.
Okay, so I'll insist that epsilon's at most a half just to deal with the small bits. But the conjecture is that it's a
For every n.
H, this case such that for all epsilon, and I'm allowing epsilon to be a function of n if you want. So it really is for all epsilon in 0, 1, not for constant epsilon. It's allowed to vary. So in particular, we can take epsilon to be some small negative power of n. So it is?
So that is allowed.
Yes, yeah, absolutely, yeah, thank you. Yeah, so not in Rödel's theorem, not at all, but this says it actually should extend all the way down. So, yeah. Good, other questions? Okay, let's not get, we can talk about that afterwards. I've got 27 minutes left to do quite a lot. Happy to talk about it afterwards, yeah. Okay, so it interpolates smoothly between Rödel and Erdős-Hajnal. And actually, okay, the reason I like it, or another reason I like it is this is how our proofs work. Okay, so all these results, when I mentioned iterative sparsification, actually we're proving this ostensibly stronger statement, kind of decreasing epsilon iteratively, and our kind of proofs necessarily go that way. Okay. Okay, another reason to like it, finally, is that Bucic, Fox and Pham last year showed actually as a nice result that the Fox-Sudakov conjecture is equivalent to Erdős-Hajnal. Okay, this is a nice, really nice, very short argument actually. So it's kind of, in some sense, in spirit, the argument's a little bit similar to the Allen-Pax-Solimoschi argument about substitution, but it's more sophisticated. You have to kind of do some more stuff. So, and you have to be more careful about scaling as well. So it's significantly harder, but it's a very short, clean argument. So, good. Okay. Okay, so how is iterative sparsification going to work? So idea is pass to induce subgraphs. So starting with your whole graph G, you pass to a sequence of induced subgraphs, smaller and smaller, so that are successively smaller and sparser or denser, whichever it is. So either they get very sparse or the complements get very sparse, and controlling the trade-off between the two. So control the trade-off between size and density. Okay. So suppose we're given, so here's the idea, suppose we're given an S, of density Y. Let's think about the sparse case, complement if we need to. Density Y and size, okay. I'd like the size to depend polynomially on Y, so some polynomial in Y times N. Okay, and what do I want to move to? So I'll move to some S prime, some induced subgraph of S, so some smaller set. So here we are. We start with a graph on n vertices. We're at S. So we've got the density is small, and we shrunk by a factor that depends polynomial on that. And now shall I look on it, T. So we move to some T, and what do I want? I want T to be smaller and sparser. So density lambda y, so for some lambda smaller than 1, I want it to be density lambda y. Okay, and how much am I willing to pay for that? Well, if I'm reducing the density by a factor lambda, I'm happy to shrink by some polynomial in lambda, so power of lambda. So size poly lambda times the size of S. Okay, so if we can keep doing this, then all the way down, the density depends polynomially on the size, or vice versa. They're tied polynomially. Okay, so this is what we'll try to do. And let's note, don't need to have a fixed lambda. Okay, so lambda could be anything within reason. So I don't want to go completely crazy and have lambda to be n to the minus 10, but as long as lambda's not ridiculously tiny, it's fine. Okay. Right. Okay, so let's prove by induction on mod H. So H is going to be some bipartite graph. That we get every bipartite H as a bi-induced subgraph, or clique or independent set of size at least n to some constant that depends on h. So this is what we're trying to do. So let's assume we're in the inductive step. Okay, and remember, bounded VC dimension just tells us that there's some bi-induced structure that's missing. Okay, and as usual, kick off with Erdős. So we may assume H is sparse. Okay. G is sparse, thank you. Okay, so the let's sort of jump straight into the. So I mean, we've kicked off here with y as some small constant, and now let's think about how we sparsify. So sparsification. Okay, so we have, let's just say, the whole of G with small density y. And then this is going to do two things. So first we'll find some nice structure. So find some nice structure. And then look at how the rest of the graph attaches. Okay.
The reason we may assume that it's sparse is like it's about VC dimension closed under complement?
Yes, yes, it is.
Is that obvious?
If you think about okay, draw the right edges in. Okay, so this was a set of size 2 being shattered. If I complement, then the neighborhood is replaced for each of these. The neighborhood on the left is replaced by its complement. And so if I get all intersections, I get the complements of all intersections. And so I have the power set again. Yeah, thank you. Yes, this is, so I'm not cheating by taking a complement here, but absolutely it's a right thing to check. Okay. Okay, I'm sort of keeping one eye on the clock. The first bit, so getting the nice structure. So, okay, what way do we have of getting kind of a nice, sort of some nice global information about a graph? Sum-radius regularity lemma. It tells us that you can break up the graph into a constant number of pieces, and then between them, it looks a bit like a random graph. Okay, so as we know, the constants are absolutely horrible. I mean, it's fantastic. I'm not dissing sum-radius regularity lemma. It's one of my favorite results, but it doesn't hand you nice constants and can't hand you nice constants. But in the VC dimension, bounded VC dimension world, it turns out that sum-radius regularity lemma, the analog is really, really nice. So there's sort of very strong results that hold. So these ultra-regularity lemmas. So use an ultra-regularity lemma. Okay. I think to save time, I'm not going to go through the ultra-regularity lemma. I'll say, again, it's another really, really nice thing. So I should mention Lovaas and Segedi. I should mention Allen, Fisher, and Newman. And I should mention Fox, Pack, and Sook. And kind of another 10 minutes, I'd write the names up and write the statement. But basically, it says, OK, what happens? So it's sort of the nicest possible thing happens. So sort of it's the version of sum-radius regularity lemma that you could kind of dream would be true in an ideal world. Right, so So we've got some epsilon that we're working with. And we have how many pieces do we need in our partition? Only a polynomial and 1 over epsilon. Okay. As usual, we can have at most epsilon proportion of irregular pairs. And all other pairs, so in other words, most pairs. Okay, and here's the really nice thing. You're not going to get density 1/2. If you have density 1/2, the embedding lemma applies, and you can get any bipartite structure you want. Okay, in fact, if you have any constant density, you can find all bipartite graphs in there, subject to parameters being appropriate. Okay, so all other pairs have density either less than epsilon or more than 1 minus epsilon. Okay, so what this says is up to some noise, this looks very much like the blow-up of some smaller graph. Okay, who knows what should make it look a bit more. Okay, so up to some noise, it looks like that, or what that would look like if I'd drawn it better. Okay, so it's this sort of it's this lovely thing, and there are nice short proofs of it as well. So again, it tracks back to nice properties of VC dimension. Essentially, the fact that if you have bounded VC dimension, you can't have many large sets that are far apart from each other, that are very different. So if you look at the different neighborhoods, you can't have lots and lots of neighborhoods of vertices that are very different from each other. And once you've got that, you've just got some small set of representative vertices where their neighborhoods essentially represent everything, and you do the usual sort of splitting up that you do with semi-radius regularity lemma. Okay, it's probably too fast for most people, but it's just a sort of suggestion that it's not. Yeah, there's a nice proof, and basically the Fox-Pack-Suit paper has a nice proof, I think. Okay, right. But the other thing that's nice about this, this is a polynomial in 1 over epsilon. It means we don't have to take epsilon to be constant anymore. So this is always a problem with regularity lemma, that you can't let your constant decrease too quickly because everything blows up. But here we can take epsilon to be 1 over log n, or n to the minus something very small if we want. Okay, so again, this is something that works on all scales. So we'll do the following. We'll get our we'll so apply this. Okay, apply with epsilon is some huge power of y. Okay, so just enough to hide all the calculations that we want to do. Yeah.
So if your density is below 1, then your pairs are actually trivially irregular because they're sparse.
Not if you have log n pieces. You can have you have a small number of dense pairs.
Oh, right, so they might be dense, but I'm saying that the regularity condition suddenly becomes useless. This is normal regularity, not sparse regularity. And the definition of epsilon regular pair is still sure.
Right, so they're either actually density close to 1 or density. Yes.
You don't care that they're epsilon regular.
But they're automatically epsilon regular because the density is close to 1.
Yeah, sorry, that's right.
Yeah.
Okay. You're not going to use the fact they're epsilon regular more than just their sparse.
No. Actually, the only thing I'm going to use about them is that they're dense or they're sparse. Yeah. Thanks. But epsilon dense or epsilon sparse or 1 minus epsilon dense. So we're actually we're really controlling the density. It's really, really small or really, really close to 1. Yeah. Okay. So right, let's apply this with epsilon to be some large power of y. So fine, I don't mind taking y to the 100 here. That's absolutely fine. Okay, so I get this nice partition. Now, I've got kind of some small scattering of annoying irregular pairs. So I'd like to drop to as large a subgraph as I can take that avoids the nasty pairs. Okay, but it's only a scattering of epsilon, so if I take something like 1 over root epsilon of these at random, I'll miss them. So it's just Turan, basically. So find kind of a collection of kind of something like 1 over root epsilon sets that have no irregular pairs. Okay, I really want to be just sparse or dense. Okay, I'm going to use the sparsity or density for two things, by the way. One, I only care that they're sort of constant sparse or constant dense. The other, I'm really going to need that it's really significantly better than y. Okay, right. I'm going through this chalk like anything. Okay, so I've got my kind of collection of sets, and these are polynomial size, but the sort of adjacencies between them, it's a blow-up of something, but I mean, with a bit of noise. Okay, so I think it's a decent chance I'll make it into the proof in the time. Okay, this is my nice structure. Okay, so let's just think, what have I got? I've got, well, 1 over root epsilon, that's some polynomial in 1 over y. So all I care about is some sort of polynomial dependency. I've got polynomial in many of them, and the size of them is n over some polynomial in my parameters. Those two polynomials, I don't really have much control over them. I mean, right, I might lose some factors of epsilon in the trade-off between number and size, but at least it's all polynomial dependence. Okay. Right. Now I'm going to look at how the rest of the graph attaches. So this was sort of the first, this was 1. I've kind of got my nice structure. Let me pick a nice color for my nice structure. Orange is nice. So I've got a tick. We've done that. Now let's think about how it attaches. So let's look at some vertex x. And okay, x might have neighbors and non-neighbors in any of these sets. Here we are, sort of A1, A2, and so on. So let's say that x is mixed on one of these sets if it has at least one neighbor and at least one non-neighbor. So I'm not talking about density. I'm just saying it has at least one neighbor and at least one non-neighbor. So it's not complete. It's not anti-complete to the set. Okay. So I want to claim that you can't be, that there's no vertex out here that's mixed on too many of these. Okay. So let's say these are A1 up to AR. Okay, so claim no vertex is mixed on, okay, so how big is R here? It's some large polynomial in 1 over y. Okay, remember epsilon was some, wherever it was, epsilon was some huge, oh, way over that. Epsilon was some huge power of y. I've sort of done some stuff, but the number of sets I've ended up with was something like root 1 over epsilon. It's still a large power of y, large power of 1 over y. Okay, so I claim that no vertex is mixed on YR sets AI. So R is some large power of 1 over y here. Okay. So y. Okay, so here's my H. So H is where I've got in the induction, or where I'm trying to go next in the induction. And I've got some vertex V here. So let's say, actually let me, okay, so I'm going to pick some vertex of H and delete it, and then look at H minus V. Okay, so suppose X is mixed on YR sets. Okay, so let's look at the pattern graph. So the pattern graph just says, or the reduced graph. So I'll take one vertex for each of these sets, and I'll have an edge if it's dense, and I'll have a non-edge if it's sparse. Okay. By the way, if we try to just apply Erdős-Hajnal here, it's not, I mean, by induction, it's not going to be enough. We lose, too much leaks out. And we actually end up with near Erdős-Hajnal, which is where Fox-Pak-Sudakov ended up. Okay. So here, let's look at the sets on which we're mixed. Right. So apply, well, look for H minus V. Okay, so two things can happen. So we don't find it. So look for H minus V in the reduced graph. Okay, so again, this is essentially a blow-up of some graph. The reduced graph is just the graph it's a blow-up of.
Just a reduced graph on these one of the
Yeah, so I've got one vertex for each of these, and then this pair is dense, I'll put an edge. This pair is not defined. This pair is sparse, so I'll put a non-edge, and then so on. So I'll look at the red graph.
V is one of the sets where it's mixed on the, or what is V?
V is just a vertex of H. So here's my H, and H is the graph that I'm working on with induction. So I'm proving by induction that this bipartite H. Yeah. So I delete a vertex. So I know the theorem already for H minus V. Okay. If we don't find H minus V in the pattern graph, then fine. That has a polynomial size clique or independent set. So poly size clique or independent set. Okay, and what does that look like? So if it's a clique, so it's polynomial size, all the edges are there, this will be something I can drop to. It's now very dense, and because I took epsilon to be some big power of y, I've still got lots and lots of pieces here, still a decent power of 1 over y. This is super dense, it's much denser than 1 over y. Similarly, if it's sparse, if it's epsilon sparse, then I can use this as my set. So use this for sparsification. So drop to this set. The other possibility, let's see if I can do it in 40 seconds, maybe not quite. The other possibility is we do get H minus V. Okay, and if we do get H minus V, so, okay, I'll just draw a picture of that. So I'm going to use that H minus V, and I've placed them as badly as I could possibly do for drawing it myself. So, what is it? It's okay, there's my H minus V. And I've got my vertex, I'll draw my vertex X here. And it's mixed on all of them. Okay. Now, what I want over here, in this case, I want V to have a neighbor in this one and no neighbors in those two. So fine, I'll pick a neighbor of x here, I'll pick a non-neighbor of x here, and I'll pick a non-neighbor of x there. Okay, I've fixed my adjacencies from x. X is now happy as my copy of V. And for the rest of the graph, well, these dense and sparse pairs tell me what I actually want. They agree with what I want. So I can just greedily find the right adjacencies. Okay, so I'll find a common neighbor there. That's a non-neighbor there. Almost every vertex here will do because the densities are very close to 1 or very close to 0, just in the right places. And similarly here. And the other adjacencies I don't care about. So I don't care about adjacencies inside the right. I don't care about adjacencies inside the left. Okay. That's a quick sketch of the claim and where it's kind of getting faster at the end. But I'll just say, what if this doesn't happen? So if no vertex mixed on many, then some AI has few vertices mixed on it. Okay, so the sum AI, so every vertex outside is mixed on a fraction of most y of these sets. So there must be one of these sets for which at most a fraction y of the outside vertices, just by double counting, at most a fraction y of the outside vertices are mixed on it. Okay, so there's at most yn mixed. Everything else is complete or anti-complete. Okay, well, two possibilities. I don't want both to happen too much. Complete, but I can't have more than yn complete, otherwise the density gets too big. Otherwise I have a vertex of degree more than yn, and I started with density less than y, or density y. And in fact, you can assume max degree is at most y times n. So at most yn complete. And then everything else, which is almost everything, is anti-complete. Okay. Right. So we have something here, a polynomial size that's anti-complete to, well, we pay some polynomial amount, and then it's anti-complete to the rest. So now we just repeat. So if we can sort of generate a sequence of these, we get something exactly right for quasi-Erdős-Hajnal. So it's kind of, we fall back into that world as well. Okay, so there's several different ways of winning. One of them is you generate a kind of a sequence of large sets that are pairwise anti-complete. That's if you get this exit repeatedly. And then the other exits were either you got this very sparse or very dense set, and that was what you wanted for what we wanted for iterative sparsification. We can just drop to that set. You have to check that everything has polynomial dependence, and then the final outcome was that we managed to embed our H, and that was the inductive step. Okay, so you sort of have to keep all these options open. I mean, generally it's a good principle to have as many ways to win as you can, but it works. Okay, I'm essentially out of time. So let me say P5, it's a sort of, we try the same sort of thing. You find a nice structure, you try to attach things to it. But both halves of that, you don't have a nice ultra-regularity lemma, so you have to do different things. But you try to do something similar, and with more work, and the cone lemma comes back as well. You can get it to work out. Okay, so yeah, so there's still lots left to do. I mean, it kind of feels we're sort of kind of just off the shore rather than kind of further into it still. Even with this VC dimension thing, it would be really nice if we get rid of, there's 3 graphs, bipartite, complement bipartite, and split. It would be really nice to get rid of at least one of those. If you could just get it down to bipartite or complement bipartite. And I suspect that might be doable. So I think that's maybe kind of one thing to point at as a possible next step, other than proving more things. Good. I've really enjoyed giving these talks. I hope you have too. So thank you very much.